Looks like the number of people down. So, welcome everybody. Thanks for joining us. My name is Sean Tavalia. I'm the academic chair for physical sciences here at Suffolk County Community College, and I'm also a founding board member for Hampton's Observatory out on the East End. So I'd like to just thank everybody for joining us today, especially for this special event. It's been a rough couple of years, as everybody knows. The pandemic had a lot of shortcomings, but one of the best parts that came out of the pandemic was it made the world a little bit smaller. And as a result, we're able to bring people in to our events from around the world. And that's just a wonderful thing for everybody. So it's one thing to be thankful for at this point. Like I said, I'm a founding member of Montauk Observatory. Hampton's Observatory. It used to be called Montauk Observatory. If you get a chance after this, please take a stroll to the site, hamptonsobservatory.com. There you'll see our upcoming events. And if you like what you see, take a second and maybe donate if you're willing to do so. As we go through this, and because I said I'm the chair of physical sciences here at Suffolk County Community College, if you are interested in the sciences and we spark an interest in you and you want to pursue that interest a little further, feel free to look up Suffolk County Community College and see what classes we have to offer. We offer a number of courses in astronomy, physics, engineering, chemistry, the whole slew of physical sciences. Mm-hmm. So today we have a special guest, Dr. Andoni Moral Inza. Andoni serves as the instrument project manager for Spain's national...
Olha, ainda não recebi nenhuma mensagem.
Oh, just mute, please.
Hã?
Please mute.
Pois não. Espero que esteja tudo bem.
Sorry about that. Andoni serves as the instrument project manager for Spain's National Institute for Aerospace Technology. He also serves as the national project manager representing Spain. In addition to his work as the instrument project manager, Andoni leads the Raman Laser Spectrometer Instrument Technical and Management Consortium of the European Space Agency's ExoMars mission. Dr. Moral Inza's work has been recognized by both the European Space Agency and NASA, and he is the recipient of the James Webb Space Telescope Significant Achievement Award. We're really pleased to have him. Andoni, I will turn it over to you.
Thank you very much. So, can you hear me?
Yes.
Great. Thank you very much. Thank you to Hampton Observatory for inviting me today. I'm really pleased, very happy to be here with you all today. Thank you very much, Donna, for insisting me to come here. It's a great opportunity for me to share with you all the things we are doing right now at INTA, Spanish National Institute for Space Technology. I will share my screen. I will share with you some slides I've prepared. All right. So can you see now?
Yes.
Great. All right. So, all right, for today, I've prepared some slides about what we do on planetary science at INTA and why we do that. It is important to understand where we are and why we are here. So, right. So, first thing I want to share with you is about the planetary exploration. Why do we explore? Why we are here? What are we doing? And which are our goals for this? And after that, I will go in a little bit detail about the Raman spectroscopy. As Son said before, I've been working on Raman spectroscopy instrument development since, I don't know, something like 14 years since I started. And today I will show you the payloads, the instruments we've been developing, and the one which have been delivered, and the ones we are working on these days and have a small overview about the future, right? So first, for me, this is one of my favorite slides. Try to answer why do we explore? Which is the reason we do this kind of work? First, because we are human beings. It is in our nature. It is in our DNA. We need to go farther. We need to discover what's the next frontier. We need to go to the poles. We need to climb the highest mountain. As President Kennedy said once during his speech during the space race, why we choose to go to the moon. Why? Because it is hard, because we need to do it. So that's very inspiring sentence. This is very inspiring speech, but it is the truth. We need to go farther. So once we reach the moon, now we need to explore we need to explore our solar system. This is the next frontier.
All right, so here is the Science National Undersea side. Do you want to just have a picture of it?
So that's one of the reasons, because we need to do it, but also we explore because we need to understand, we need to answer one of the most important questions we have as human beings, some kind of philosophical question, which is, are we alone? Why we are here? Why we appeared on Earth? And are we alone? Are there any other living things out of our frontiers, of our planet? So we need to try to understand, to answer these kind of questions. So that is why we need to explore. This is some kind of an obligation, a must. We should try to answer this. And then, so next question would be, where should we look at? Some years ago, not that long away, we thought that the solar system was a very boring place, with no life at all. We thought that if any kind of living thing was sharing the universe with us, would be very, very far away from here. But now we know that maybe that is not exactly true. Maybe there was, or maybe not now, but in the very early times when the solar system was formed, several environments which could have the proper conditions for starting life, or what we understand which is life, could take place. So now we are knowing in much more detail the different planets and the different satellites we are with us, and we feel that very, very interesting things could have happened in the past, or maybe even we need to look in much more detail under surfaces and looking for liquid oceans and so on, and we feel that proper conditions could have happened in the past, or at least similar conditions to the ones that we found on Earth during the early stage of when forming, something like 2,000 million years ago. Very similar environments could happen. So we really would like to look at every single place in the solar system where very similar environments to the ones that we had once on Earth. So, and how we explore, which are the steps we usually take for this kind of planetary exploration. All right, this is how we did on Mars, and this is a pretty good example. First, something like in the 19th century or something like that, we did some observation from Earth with very primitive telescopes. We were able to see the Martian surface and we can even appreciate some kind of channels, some kind of even caves for some. And that allow us to imagine people living there or something like that. After that, we try to go as much close as possible with some kind of flyby devices. We wanted to try to take a picture to the closer possible to its surface, and what we obtained there, what we observed there, we realized that all right, this was not some kind of a living planet or something like that, but very desertic and very harsh environment was there. But this allow us to figure out, or to want the willing to go there. So then we try to get some devices on orbit, some probes on orbit, in order to get as much pictures as we can. Later, we wanted to we land, and so once we were there, we take pictures, and we we confirm what we knew from orbit, that it was a very harsh environment, very desertic one, but we were prepared to do some tests looking for some kind of life there. This was our first goal to look for this. And all right, this was the last Viking mission finished in 1977, I guess, and up to until 2000, we were not able to go back or to reach again Mars with the all right. We went there with the spirit and opportunity. These twin rovers that allowed us to move on the surface. We were not just fixed on one point. This allowed us to move, to rove over the Martian surface, and this showed us quite interesting things on that. This make us feel more interested on this, and the final reach was the NASA rovers, very well, Curiosity and Perseverance. But this was not enough. We observed the surface of Mars, but we wanted also to go in a different dimension. We looked for, we flew some drones in order to understand better the Martian atmosphere, the lower Martian atmosphere. It was also planned to with the ExoMars mission to look below the Martian surface, looking for those areas which were not affected by cosmic radiations. In case we felt that some kind of very old organic traces could be preserved, these would be under the Martian surface. So this was the main goal of this ExoMars mission, European and Russian mission. And next steps will be, for sure, Mars sample return. It is, we are able to develop and to put on Mars very sophisticated instruments, but it's not the same as in case we are able to analyze them at home. So we want the samples to be sent back to Earth. And this will happen until we are able to put a man or woman on the Martian surface. So that will happen for sure, but it will take a while then. So this is how planetary exploration typical steps are. So what kind of instruments do we develop, or what we need? It depends on when are we and which are the objectives we are looking for. If we are looking for life, or first we looked for water, then we we looked for habitable environments, and then now we are directly looking for signs of life. But for to understand the presence of life, but we need also to understand how Mars works. So we need to map, we need to understand the climate, we need to understand geology, and that's only when we are ready, when we know all this, we are able to understand pretty well all these questions, we will be ready for the human exploration. We need to make sure there are not big hazards for a human mission. We need to be ready to develop our own consumables, you know, the water, the oxygen we need for staying there for quite a long while. And then we need for sure to make sure people that reach the Martian surface are able to come back home. So for this, we need to develop different types of instruments, instrumentation, cameras, sensors, spectrometers, depending on where are we focusing, where is our aim for understanding different parts. We need to develop different instrumentation. So, as Son said before, right, I'm here because I've been the RLS, the Raman Laser Spectrometer project manager for last 8 years. This instrument, which has been part of the ExoMars mission. But as I said before, I've been my expertise is in this spectroscopy technique, the Raman one. So a brief overview of how this works. Indeed, this was discovered in 1928 by an Indian scientist, Chandrasekhara Raman, which published this inelastic scattering effect on samples when they were irradiated by light. He published this effect, the discovery of this effect in Nature in 1928, and he obtained the Nobel Prize in 1930 because of this discovery. So this was quite impressive. This was quite important on that time. So how it works? All right, you can, if you irradiate, if you illuminate a sample, if it is better if you do it with some kind of monochromatic light, you will there will be some energy that will be scattered in a quite elastic way. So it will jump to an energetic level and come back to the same one. But a very small part of this energy will be inelastically scattered, and this light, this signal, is the Raman signal, and this it is some kind of a footprint, fingerprint, sorry, of the molecules what we are observing. So this is quite powerful technique then. So we obtain a lot of information, not only about the chemical composition, but only about the molecules, molecular composition, which makes a big difference. So this is why this was such important, and this is why this technique has been tried to make it for use in space for several years. So as said before, this technique, this Raman spectroscopy technique, it is very fast indeed. We are considering this kind of analysis we do in our lab, but also what we do in space. We can obtain this information in several seconds, for sure, no more than few minutes. We can obtain the overall information that we can obtain from this sample. It is non-destructive, so we can apply it as many times as we want, and this also allows us to combine this technique with some other techniques. So if you do your work on the lab, you don't use just one single technique. You use several ones in order to be able to fully characterize your samples. So it is, as I said before, it's a very powerful technique. It provides a lot of information about the molecular composition. So that's why it's used for mineralogy, but also for biomarkers and so on. It is pretty low power consumption technique. It is pretty light instrument. This is a pretty light instruments technique. We don't need very big instrumentation. We don't need a big amount of power or energy to operate this kind of instrumentation. So this makes very we all want to have one of these, whatever the mission we are in our payloads. We can adapt it to different working distances. We don't need to prepare the sample. We don't need to clean it. We don't need to crush it. We don't need to use liquids for it. We can do it, apply it directly on whatever the sample it is. And it is easily combinable with some other techniques. So that is why this makes this technique ideal for planetary exploration. So quick overview of different payloads, different instruments that have been ready for fly or even on flying right now. This is the RLS, as I said before. This is the instrument I've been project manager for this long. This is the Raman laser spectrometer. This is an instrument that it was, or right now, let's say it is within the ExoMars Rosalind Franklin rover. It was delivered in 2018, the flight model. As you may know, this mission at this point, this ExoMars mission at this point has been suspended, formally suspended because of the, it was expected to be launched something like 1 week ago from Baikonur, from Russia, with a Russian launcher, with a Russian rocket. And also Russia, Roscosmos, the Russian agency, had pretty important participation on the rover with the radioisotope units. And after the war in Ukraine, this collaboration with Roscosmos, has been cancelled, and right now the mission is formally suspended. We'll see what happens. But this was delivered in, as I said before, in 2018, ready for its launch in 2020. Some problems with the entry, descent, and landing systems made it delayed the mission to 2022, and now we're waiting. Another big instrument, you know it very well, SuperCam. This is Raman and LIBS and infrared and microphone and visible camera and everything in one instrument. This is a huge instrument, and indeed it has the remote Raman capability, which is working right now on the Martian surface, and we expect it to be working for a lot of years. Also, in the Perseverance rover, in the robotic arm, it's placed a smaller instrument. It's called Sherlock, which uses ultraviolet illumination for this Raman spectroscopy. It is working right now, also in the Perseverance in Mars. And this is another, the RAX instrument, which is the very last one, which has been already delivered to Kenes for the MMX mission, the Martian Moons Explorer mission. It is a Japanese mission from JAXA, and this mission, which is some kind of orbiter around Phobos and Deimos, Martian moons, that will deploy a very small rover, very small, I mean this size rover, on the Phobos surface, and it will be on board this Raman spectrometer for analyzing Phobos surface, trying to understand the origin of Phobos and its composition. So, all right, I just want to show here that we are at some point in different levels, that's clear, but we've been involved in up to 3 of the 4 instruments, Raman instruments, that are right now in flight or ready to be flown. The RLS is the main, it's our main contribution for sure, but we also were in a very small contribution to SuperCam with the calibration target for which is some kind of a different target, different samples placed in a metal sheet in the outer surface of the rover, which it is used by SuperCam to wherever it's going to be operated. It points to the calibration sample, takes several spectra, calibrates itself, and then to start operating on Mars. And also with the racks, we've been deeply involved. We have developed the laser, which is used for the Raman instrument, together with DLR, the German Aerospace Center. So, all right, this is, let's talk a little bit more about ExoMars mission very briefly. There are up to 9 different payloads. As I told before, 2 of them are Russian. They will not fly for sure. And the other 7, there are different contributions from different ESA countries. So the RLS, it is placed within the analytical laboratory drawer, which means that a very, challenge, one of the main challenges of this mission is that we were supposed to be able to analyze the same sample obtained from the drill of the rover up to by 3 different instruments, an infrared named Micro Omega, a French instrument, a Raman RLS, and the MoMA, a mass spectrometer, which is a German and French instrument. So this was a quite important novelty about this, because 3 different instruments will analyze one single sample in order, first the infrared, then the Raman, and the last the MoMA instrument. This made this mission very special, and these samples obtained from up to 2 meters from below the Martian surface. This is why these are the key points of this mission. All right, briefly overview of the Raman laser spectrometer instrument. There is a spectrometer. There is an optical head which is pointing to the crust sample obtained from below to the Martian surface, and there is an electronic box where different power boards, processing boards, and also the laser is placed there. I will not get into much detail about how a Raman instrument works, but if some of you are interested, I would love to go in more detail later on. All right, this is how the contributions this was a quite complex consortium. It was led by INTA, by Spain, but also we have very important contributions from IRAP, which is a French space institute placed in Toulouse, in France, with important contributions also from UK, from University of Leicester, and Rutherford Appleton Laboratory Space Center placed in Oxford, and also some minor contributions also from Germany, from OHB, and so on. Different for the science, a lot of universities have been involved in preparing this science to be obtained by the instrument. Again, as you know, as I told you before, our main expertise, our main background is developing payloads. So this specific instrument, the Raman instrument, took us several years of development, first as a breadboard. I think it's important to remark here that the Raman spectroscopy was, let's say in another way, the first mission which had an approved Raman instrument on board was the ExoMars mission. So for sure, we will not be the first one in flight, but it was the first one approving this kind of technique. And why? Because even for the Spirit and Opportunity rovers, and also for Curiosity rover, this was planned to have a Raman instrument on board, but at the end, the difficulties of the optics of the spectrometer, and the difficulty mainly on the laser, which is the excitation source, which need to be extremely stable all along thermal excursions, extremely narrow width with a peak of excitation under also under different thermal environments. This made this technique was not able to fly on these other missions. So this is why this took us this long, up to 4 years, developing different parts of the instrument, key parts, as you know, the spectrometer and the laser. And then finally, once we have some kind of consolidated design, we were able to move on and start building what was the STM, the structural and thermal model, EQM, the engineering and qualification model, and finally a flight model, which is the one which was delivered by the end of 2018 to Torino in Italy, to the rover team, which were the responsibles of integration of the whole rover. All right, here just few pictures about how the ALD, which is the analytical laboratory rover, where all these 3 instruments and the ultra clean were integrated together with sample crusher, sample carousel to allow obtain samples with the drill to be crushed in the very small grain size and placed under different instruments for its analysis. The one which is hoisted here is the ALD, and finally you have here the final results of the the Rosalind Flying Clean rover. One thing is, all right, I don't know if you are aware of, but these days Europe is negotiating with NASA about the future of this rover. We feel that for sure will not be launched with Russia, but some negotiations are ongoing with NASA in order to, if we can arrange some kind of agreement with US in order to them to launch this rover and deploy it on the Martian surface. That will not happen earlier than 2028 and maybe 2030, which means that science results won't be here before 2030 or 2031. But anyway, again, we feel that the science case this rover will be able to obtain, it is very important to understand how Mars was formed, how was the original environment that Mars had, very similar to the one we had here on Earth, with liquid oceans, dense atmosphere, warm temperatures, so also magnetic field. So this happened. This was on Mars. So, and again, trying to answer previous questions, if life happened on Earth, why not on Mars? Maybe there's nothing living there right now, but in the past there could be some traces for this. And right now I'm going to explain briefly about the MMX mission. This, as I said before, this is a JAXA, a Japanese Space Agency mission, which is its goal is to study Phobos and Deimos, which are Martian natural satellites, trying to understand its origin. It is pretty weird that Mars is very red, Phobos is very black. Why? This asteroid, this could be some kind of trapped asteroid by the planet, or this was formed by some kind of collision. Trying to understand this is the main reason for this mission, for this Japanese mission. And as I said before, the main probe, the main orbiter, Japanese one, will deploy at some point. This mission is expected to be launched in 2024, reaching the moons, Martian moons, by 2025. And the rover hopefully could be deployed on Phobos surface by 2027, something like that. And after that, it would start roving and doing some measurements, trying to better understand. For the Japanese mission, it is also expected to do perform some kind of a sample return of this Phobos regolith back to Earth, the way they do for the Hayabusa missions. So it will be a very nice mission to try to do this ground truth analyzing on this Phobos surface and trying to match results obtained with the ones obtained on the Martian surface and with the samples returned to Earth. So that is a very, very interesting mission. This is what our main contribution to the mission, as I said before, is a very tiny laser. This weighs no more than 60 grams. It is redundant. We have two different channels for the same output in case one fails, or we can design different powers, different wavelengths on different channels. So it is perfectly controlled on wavelength, on power. So this allows us to take part in these kind of missions. And this is, let's say, this is our I don't know how to say, our best product we have at INTA. And this is why we take part in these kind of missions. So now, what about the future? These are what we feel next challenges in planetary mission. For sure, going back to Mars. For sure, going back to icy moons, Europa, Enceladus, Io. There are lots of very interesting worlds there we want to explore. But first, I think you all know very well. First, we will go to the moon. With this huge program, which is the NASA Artemis project. But again, why try to understand why we are going to the moon is all right. You have a clue in this picture there. This small red marble behind the moon is Mars. So we need to go to the moon in order to train to be able to put somebody on the Martian surface. So this is the key. We need to go to the moon to train ourselves, to practice our techniques, to put everything ready, to have permanent bases on the moon in order to make an easier travel to Mars with a lot of things we need to put there. So this is why we're going to the moon. We need to, and after, more than 50 years since we were there last time, we need to train again to get used to go to the moon and go back to Earth. That is a must. So, all right, this is short. I want you to show how things we're doing right now. We are involved in a Pangea program. This is an ESA program, which it is focused on developing, instruments for astronauts to be able to do on-site analysis on the moon in order to get for different try to identify different minerals, try to identify different compounds that could be used for or could be useful for exploration. So that's mainly focused on the ISRU, in situ resource utilization. We need to be able to use what we found wherever we go in order to be able to stay there, to live there, and to make sure we are able to come back. So that's the goal. That is why we need to learn how to do this. And for sure, for the new payloads that we all foresee to develop, we need to improve. We need to make lighter instruments with which comes some much less energy, much less power. We need to we will have difficulties for the power, but also for the data we want to send back to Earth. So we need to be at some point autonomous. We need to have to develop some kind of artificial intelligence tools in order to make sure that we are sending back what we feel it is the best results we are obtaining. We need to improve the capability of the performances of our instruments, and we need to develop instruments prepared for very harsh environments. So when this happens, this is applicable also for Raman. We want to be able to operate Raman not directly on contact, but at different levels for remote and in the order of meters at some point of very contact instruments within a robotic arms with some kind of centimeters distances, but also for millimetrical distances, we can go in much more detail. So combining these three different techniques on one single instrument will allow us to reduce the mass, the power, the volume we need to put on a platform, on a rover or wherever. Also, combining techniques. I'm talking about Raman, but this is applicable to any other. This will allow us to have much more interesting science, much more powerful science. This is 1 + 1 is higher than 2. So that is why this is that interesting. And in this way, what I talked before about the Pangea program from ESA, we are right now developing 2 different breadboards for astronauts. Breadboard and LIPS combined instrument, combined breadboard, but also breadboard and XRF, X-ray fluorescence instrument, spectroscopy instrument. So this is where the future is, and this is what we are doing right now. And I think this is my last slide. All right, we need also, this is a more internal thing. We are right now developing, trying to develop new lasers, much more powerful. We can control them much better in different wavelengths, with different power output power. So this is what we are doing right now. All right, so I think this is all I have by now. I would be very happy to try to answer any questions.
We have a couple of questions in the chat. I'll try to get them in order in which they came in. The first one that you have is from Irving Tiffany. I've heard a wide variation of estimates of how soon we can send humans to Mars. What's your estimate?
Wow.
Put you on the spot.
I don't know, what happened in the 60s, we are able to do whatever we want. It is if in case we are in the mood to pay the bill, that will be easy, and we need to be prepared for that. I think that we are living now a very, very interesting period, with this, I call this a new space race. We are not racing against anybody now, not even with China. We are just feeling the excitation of discovering new things, and this coming back to the moon, I think it is a very, very first step, very, very interesting step. And I am sure that we are obtaining amazing images every day coming from Mars. This last mission, DART mission, we are able to, to move planetary body. This was never done before. And so we are showing amazing capabilities. And so we are there. I don't know when. I'm not sure. I will see it with my eyes, but for sure my sons will do. I don't know.
So the next question was from Patria. What was your reaction when NASA hit the asteroid? And is anybody from ESA or from your group involved in that work?
Yeah, people from my logo in my presentation. It's INTA, which is the National Institute of Technology, Aerospace Technology. But also we have the CAP. CAP is an astrobiology center, which is participated at some point by NASA. This is one of the NASA have very few, but very important institutes, astrobiological institutes around the world. And the CAP, this one in Spain, was the first one. And people from them, people from CAP, they are deeply involved in this DART mission. Not only for DART, but also for HERA. HERA, you know, is a European mission that will go back in 2024 to this asteroid to analyze the crater formed by this impact and try to understand, you know, try to, you know, finish the loop for the analysis. We need to understand which is the material these asteroids are made of in order to, so we need to understand which is the hardness of these bodies. So, and then we will be able to predict what kind of, or which is the amount of force we need to do in order to move them, or how the size we need to, of the spacecraft we need to impact on the surface in order to, you know, deflect its trajectory that much. I don't know. So yes, people from here, everybody here very excited about this DART mission, but it's not done. We will continue investigating about this, yeah, for sure.
Another question from Paul W. Does Raman spectroscopy only detect the surface minerals? Can molecules, can it do any penetration, depth penetration to see what's below the surface?
No. Well, it depends on the crystallinity, crystallinity of the sample. I mean, if we can inject the light deeper, we will excitate the whole sample. If this is an opaque surface, we will only be able to excitate this part. But you know, for the RLS, for the ExoMars mission, the samples obtained with the drill, they were a very, you know, small cylinder, few centimeters long and 1 or 2 centimeters wide. The point is that we crushed this sample. Why? Because we wanted to have some kind of heterogeneous sample in powder, and because this will allow us to investigate not only the surface of the sample, but also it was demonstrated by some mathematical models that crushing it and deploying it with these different shots, let's say this way, on the container, which was placed under every single instrument, allowed us to detect almost all the components that this sample had. So, all right, this is not all right. The answer is no. We are not able to go into into depth of the samples, but there are different ways of handling this. You know, if you are able, also, I'm thinking about SuperCam. If you are able to take an image of that's helping you for context, for that allows you to say, all right, I want to point that black dot there, and because that is the point I'm interested on. You know, normally samples are not that not homogeneous, but you can select where you want to obtain your sample, the science.
Jeff Katz wants to know, are you using shifted excitation to deal with fluorescence? And I think he has a follow-up to that.
Yes, that is one of the most promising techniques, which is right now we are working with that on the lab. Yes, that's you know, fluorescence is our biggest enemy for Raman spectroscopy, and trying to reduce it is where we put almost all our efforts. And yes, in case we are able to excite same sample with different wavelengths, and we can subtract results obtained from each of them, this has been demonstrated as a very powerful technique in order to reduce this fluorescence. So this is one of the things we are doing, since we have the control of our laser. So that's yeah, that's one clear way forward where we all think we must look forward. Yeah.
So I love the questions from students. So Alejandra is a Spanish aerospace master's student who would love to work in the planetary exploration department at INTA. He's wondering what advice could you give him in order to join the
All right.
institute?
I would say, I don't know. We have lots of European students working with us as part of finishing their master degree. But I don't know how this works with US students, but I would say I would suggest you to try ask in our webpage, www.inta.es, and ask for, there's a department of, how do you say, training, formation, I don't know. And you can ask there. They are used to deal with people from students from very different places. So ask there directly. So maybe we won't be able to pay you for your expenses here, but we will be happy to take people from different places for sure. It is very, it's enrichment for everybody.
Isabel has a question about lasers, and you mentioned developing strong lasers. How do you go about doing that? Is it an increase in frequency or using a different type of electromagnetic wave?
All right. Let's say that it is also dependent on the spot size we are pointing your laser. It is not that in case you want to focus on a small grain in order to put a lot of energy there, the risk is that you can damage the sample. So this is not critical in case you are alone, you want to, or you have access to a new different sample. The case we have on ExoMars is that we are working together with two other instruments, and so we are not allowed to damage the samples. So so that's the point. But yeah, you can increase your power, but that will increase for sure your fluorescence, and yeah, at some point this is tricky. You need to trade off at some point. Yeah.
There's one more follow-up from Jeff. Jeff, do you want to unmute? You can. I don't think we have any other questions.
Yeah, hi, can you hear me?
Yes.
Okay, yeah, I've been working a lot on Raman spectroscopy on Earth and sample damage, fluorescence. What I was wondering is, there other problems you're experiencing, like trying to detect weakly scattering analytes when there are a lot of other interfering, more strongly scattering analytes? Any other kind of issues you can elaborate on?
This is strongly dependent on your instrument resolution, let's say this way.
Instrument resolution, and also attendu,
Sorry?
light capturing capability, attendu.
Yeah. How can you distinguish two very close Raman peaks coming from a single sample? I would say that this is key in order to and at the end, Raman spectroscopy is very powerful, but this is not all. What we do here on Earth is, for sure, you need at some point supports from different techniques. That's the advantage we have here on Earth, that sometimes you are not able to distinguish with a single Raman instrument the analysis you are doing. You need to combine this with all the different techniques. But yeah, I would say that our main goal is to improve our resolution. That's what we are. This is what we allows us to also for sure the accuracy on the, but that you can characterize that. Working with databases in order to have a big library of different samples of allow you to make sure what you are analyzing. And but again, in case you are, I don't know which is your field of work, but in case you are working with Martian mineralogy, you need to go to those places where you feel that you will find things similar. This is it is not easy for a blind test, let's say this way. You need to know, you need to have some information, some context information for this, some powerful databases. That's the point, or be supported at some point by different techniques. I don't know.
Okay, great. Thank you so much.
You're welcome.
I know it's getting late for Andoni. So one more question, or Chris, go ahead. If you speak up, they should hear you.
I just have one more about Mars, pertaining to life, possibly. Is there really a monolith on one of Mars's moons? And there's also been claims that there's a megalithic structures around the crater Aerospace. I don't know if I'm pronouncing it right. Aerospace. I just was wondering if that was true or just, for publicity.
So did you hear the question, Andoni?
Not very well. If you can repeat it, I would appreciate it.
Yeah, the question is, a student has heard that there are monoliths on some of the moons and wants to know if that's really true, the moons of Mars. Are there really monoliths or megaliths that were created, or is that just something of mythology or conspiracy?
No, I think that, all right. I think we have I don't know how to say, we have pretty nice scientists, pretty nice instruments working there. You can be confident of what we are obtaining. It's incredible what we are doing, what Perseverance is obtaining, what they are doing, and I'm pretty sure that all right, you can trust on them, and they are really doing a great job. So.
Hey, thank you, Andoni. Thank you for joining us. Thanks for taking time out of your evening to be with us. This was a great presentation. We loved having you. I hope you'll consider coming back at some point in the future. Give us some updates in your work. Thank you, everybody, for joining us. I hope you enjoyed the presentation. And like I said earlier, if you enjoyed what you see, please take a second and join us at hamptonsobservatory.org and for our next future events. So thank you.
Thank you very much, Sean. Thank you very
Thank
much.
you. Great talk.
For taking me here, and